So good morning, everyone. Today is a very nice day, and I'm very happy to have Professor Rosa Palacín here. She will be talking about batteries, and I will be summarizing a little bit about her trajectory. So Professor Palacín is the Deputy Director of ICMAB. She has been working in batteries for a long time, and she has been mainly working on solid-state chemistry and electrochemistry applied to battery technologies, covering technologies either commercial from nickel and lithium ions, or pre-commercial as sodium ions. She has co-directed the Alistor ERI project, and it's currently the Vice President of the International Battery Association and member of the International Meeting on Lithium Batteries Executive Committee. She has contributed to many roadmaps for the use of batteries at the European level. And I'm very happy and very glad that she accepted to be our speaker today. So thank you very much, Rosa, and the floor is yours. Thank you.
Thank you very much, Nuria. I'm really glad to come to ICSIC, even if it's virtually for the moment. But at least this is better than nothing. So the topic of my talk is what we have been involved in the last years, dealing with the development of new technologies, of new battery technologies. So hopefully you can see my screen now. Is it okay?
Yes, it works.
Okay. So then, so first of all, a short introduction about why we were involved, or why we decided to work with new battery technologies. So essentially, the past of batteries is well known to everybody. It comes from the findings of Volta and his controversies with Galvani about the origin of electricity. And in fact, the development of the first battery was a way to show Galvani that electricity didn't have anything to do with an animal origin. And even though this was really a fundamental research, the practical prospects of such findings were soon realized, because it was a possibility to create a device which would deliver electricity upon demand. This was published in the Philosophical Transactions of the Royal Society of London. This was a breakthrough at the time. And this design was a little bit cumbersome, and the capacity and so on was very low. But soon other primary batteries start to be applied in fields like the telegraph, which were booming at the time. And about 60 years later, the first rechargeable battery technology was born, the lead acid battery technology, which is still in use today. We have them in the cars to start the combustion engine cars. So then soon after that, the nickel technologies came with the development of nickel cadmium technology in Sweden, and then Edison in the US with the nickel iron and so on. But when we come to present, I guess we would all agree that the present battery technology is lithium ion. So this technology was born in the early 90s, and the parents of this technology received the Nobel Prize in Chemistry in 2019. And it essentially is based on two different electrode materials that are able to intercalate, and they intercalate lithium upon charge and discharge. And typically one is using lithium cobalt oxide as the positive electrode. This was in the first generation of lithium-ion technologies, and carbon and soon graphite at the negative electrode. Since then, this has turned into a family of technologies, because different materials are used, for instance, on the positive electrode material. So different types of lithium-ion batteries exist. But then when we are looking at the future, it is much more difficult to predict. So even if you were asking battery researchers or battery engineers or battery specialists, you would probably get different answers about what will be the technology or the technologies in the future. So one of the things which is extremely relevant nowadays is that batteries are embracing fields of application at a larger scale. For instance, I was mentioning that the lithium-ion batteries were developed in the 90s, and they helped a lot in the development of portable electronics, and it was a synergy between the product and the application, because the development of portable electronics also triggered improvements in the lithium-ion battery technologies. But finally, for those devices, you need one or a few cells connected, and the energy is in a small amount, watt-hours, I would say. When we think about electric vehicles, which is nowadays booming, so to say, then we go to the kilowatt-hour scale, which is thousands times more. And here, of course, the energy density is relevant, because we want the car to have a long range, but there are other features which become also very relevant, such as safety, because this is a big battery and there are people inside the car. The battery cost, because we cannot afford the same level of overcost that we pay for portable electronics, and also the lifetime. Because finally, for portable electronics, we are changing our mobile phones every, let's say, 3 years, but we would expect the battery of our car to last as much as the car, at least. And we can even think of a larger scale application in the grid. And for instance, there is a Tesla lithium-ion battery installed in Australia, and this is in the megawatt rate. So this is 1 million times more. So you can imagine that upscaling a technology from watt-hour to megawatt-hour has a lot of hurdles to improve and challenges, and it's not that trivial. And one of the things that one needs to consider is sustainability. So if we're thinking of making really very big batteries on a very broad scale globally, we need to think at the energy and water footprint of the technologies. Of course, we need to consider recycling. This is compulsory. But finally, when we are considering the development of the technology from the early stages at very low TRL level, we need to think about the scarcity of materials and try to use abundant materials and avoid the use of critical materials. So this is a periodic table of the elements according to relative abundance that I used to show in the past, because typically the area is proportional to the abundance of the element, but it turns out that this is not true, even not at a logarithmic scale, especially for the case of rare earths here. So this would be a much more realistic image. So you see that if we are finally targeting abundant elements, there are not many choices. So if we're thinking of building new battery technologies that could be as successful as lithium-ion technology, there are two relevant concepts to mention. So one of them would be to mimic the lithium-ion concept. So one can think about the metal-ion technologies. So in this case, you have two electrodes that insert and de-insert, for instance, metal ions, so that react reversibly with metal ions. So in this case, instead of having lithium plus ions as charge carriers, you would have sodium, magnesium, potassium, calcium, etc. And in this case, the energy density is finally dictated by the potential difference between the two electrodes. So it is not really related to the nature of the metal, but one has to bear in mind that the limit for this negative electrode is the limit for electrodeposition of the metal. So this is one thing. And another thing relevant to mention here is that for the charge carrier ions that have a charge higher than 1, there may be some issues both for the migration of the solvated ions in the electrolyte and also for the migration in the solid state. And about this concept, I will mention the development of sodium ion as an example. One of the advantages here is that you can take advantage of the know-how developed in the lithium ion technology. And then you can expect a faster progress. And another concept which is interesting is the use of metal anodes. So in this case, the negative electrode would be a metal. And here you can see a graph showing the gravimetric capacity in green for different metals and the volumetric capacity in gray. So you see that gravimetrically nothing compares to lithium ion because lithium ion is very light. To lithium metal, sorry. Of course, when we move from lithium to lithium ion, then we use graphite as negative electrode and the capacity is much smaller. And this is due to the fact that lithium metal grows forming dendrites. And this is an issue for the battery safety. But then finally, some metals would be better than graphite if we were able to safely use them. So sodium also has issues with dendritic growth, but then if we could use multivalent metals like magnesium, calcium, or aluminum, the capacities would be higher, especially volumetrically, because lithium is not very dense, and especially for aluminum, if one could exchange 3 electrons per mole of metal. But energy is the product of capacity and voltage, so let's have a look at the reduction potential of those metals. For aluminum, it is moderate, so it is not that interesting. Magnesium is slightly lower, but then what is interesting is that calcium is very close to lithium and sodium, so very negative reduction, standard reduction potential. So promise of very high energy density if we are using metal anodes. So in this case, the problem is to stabilize those anodes so that they can be safely operated. And so there are also many researchers working, for instance, trying to stabilize lithium metal anodes still, either in all solid state batteries or lithium sulfur or whatever. But in this case, what I will focus on is our works on calcium metal. So now coming to the first part of the first topic I would like to discuss with you, sodium ion. So the background is that sodium is very abundant. Here you can see the difference on the abundance on the Earth's crust. And of course, there is plenty of sodium on the sea. So it is available for many countries, I would say. Then the standard redox potential is rather similar, as you have seen. And one technological advantage is that sodium does not form electrochemically any alloy with aluminum. This is the standard scheme of a lithium-ion battery. You typically have the electrode materials, which are powders mixed with a binder, polymeric binder, and carbon black to enhance electronic conductivity, tape casted on metals. And usually you use aluminum as current collector for the positive electrode, but for the negative electrodes, you're forced to use copper, which is more expensive than aluminum, because lithium forms at low potential alloys electrochemically with aluminum, so you cannot use aluminum. In the case of sodium, this is not the case, so ideally you can use aluminum as current collectors for both the positive and the negative electrodes. And this, in principle, could also enable the transport of those batteries short-circuited. And this would release some of the restrictions for the safe transport of batteries. This is something that is still being checked with especially by startup companies building those cells. But this is really an interesting advantage. So the fact that lithium and sodium have similar chemistry, as I was mentioning, allows us to use all the know-how that we have from the development of the lithium-ion battery technology, and this should foster the progress. But at the same time, we need to be aware of the existing differences between sodium and lithium. The fact that the ionic radius is different, this will result in difference in coordination preferences, and so in crystal chemistry, and some electrode materials would be rather different. Then the polarizing character as a result of having the same charge but different radius is also different. This will impact the diffusion and the kinetics. And finally, also the solvation energy. So the solubilities of lithium and sodium salts may be different. And this will impact what is called the SEI, the solid electrolyte interface, which is a passivation layer, which is built on the surface of the negative electrode, because this is operating at very low potential where the electrolyte is not stable. So the electrolyte decomposes on the surface of the electrode, pretty much protecting it like aluminum oxide protects aluminum for oxidation. But then if these compounds that are formed there are soluble, then the protection really will not work as well. So one example of those trends is here, as I was mentioning. Typically for the lithium-ion technology, one is using graphite, and the typical electrolyte is lithium hexafluorophosphate in a mixture of alkyl carbonate solvents like ethylene carbonate and dimethyl carbonate. And lithium iron phosphate, for instance, is one of the electrode materials which have been used commercially. So one could naively think that one can develop a sodium-ion technology just changing lithium hexafluorophosphate by sodium hexafluorophosphate and lithium iron phosphate by sodium iron phosphate. But this is not the case. First of all, graphite does not intercalate any sodium. So the only carbonaceous anode that one can use is hard carbon, which is a disordered carbon. And then when one synthesizes sodium iron phosphate, the crystal structure is different from this one, and there are no pathways for the diffusion of sodium ion. So really, if you want to prepare the same crystal structure, it is much more cumbersome. You need to prepare the lithium derivative, extract lithium, so it's not really that easy. So we need to bear in mind that both technologies would be alike, but there will be significant differences. So this technological concept is not new. It comes from the early days of intercalation chemistry, where intercalation of many ions in inorganic structures was studied, as lithium, sodium, and many others. And even some first proofs of concept were given in the early 90s, but then the field was abandoned due to the advent of the lithium-ion technology, so everybody focused on that technology. But here you can see some results of a full cell using a sodium-lead alloy as negative electrode and sodium cobalt oxide as the positive electrode, and using either liquid electrolyte, sodium PF6, as you can see, or even a polymer electrolyte working at 100 degrees. And the topic was rediscovered about 10 years ago, more or less, coupled to the scope of building new technologies, more sustainable, of realizing that lithium was scarce and we would need a lot of lithium to cover for all those new applications and so on. And here you can see this is from an old review. It was for 7 years ago. It was published 7 years ago, but still you can see this is a graph showing the capacity and the potential for some materials that have been suggested as positive electrode materials. So if you did a full cell with those positive electrode materials and hard carbon, these are the energy densities that you would get. And here you have as a comparison the graphite lithium manganese oxide, which is also a commercial lithium-ion technology. So you see that for many materials, the energy density would be on par with commercial lithium-ion batteries. And here it is the complementary graph. So this is materials that have been suggested to be used as negative electrode materials, which when coupled to those layered compounds as positives, they would have this energy density. And for some of them, again, it is comparable to commercial lithium-ion. So there are essentially two types of positive electrode materials. The first are very similar to the lithium cobalt oxide I was mentioning for lithium-ion batteries, which nowadays has also diversified a little bit. And in some cases, instead of only cobalt, we have nickel and manganese as well. So the so-called NMC, they have a layered structure with edge sharing a phase sharing metal oxygen octahedra, and in between the lithium ions are also coordinated, typically octahedrally, or in some cases also tetrahedrally. And here, for the case of sodium ion, one can form very similar phases, but in this case, the coordination is sometimes also prismatic as a result of the larger radius of sodium. So in this case, those materials are really very similar. Air stability can be an issue, but still. But then for 3D structures, typically the crystal structures are different from those existing in the lithium-ion technology as a result of this 3D character, because the coordination sides are depending on the radius of the ion, and then lithium and sodium have different radius, but still this is one of the materials which has been successfully used as positive electron materials for sodium-ion batteries, which is this sodium vanadium fluorophosphate. And there are French groups by Christian Masquelier, Laurence Groguenec that have worked a lot with this compound. On the negative side, as I was mentioning, only hard carbon can be used. This is prepared by pyrolysis of solid precursors, and typically you get these diffraction patterns. This is a very disordered material consisting of graphene sheets between 10 and 40 angstroms of size, and then stacked between 2 and 3 layers. And this is the voltage versus capacity profile. It has a very low operation voltage, slightly lower than graphite, so there is some risk of sodium plating, which needs to be mastered. And the main issue with this material is that there is a lot of irreversible capacity on the first cycle, but this can be tuned typically with tuning the microstructure, and also this is in turn determined by the pyrolysis conditions, and also the electrolyte use has an effect on this. So just to show you, we did some laboratory prototypes with the hard carbon we prepared and sodium vanadium fluorophosphate that we got from our colleagues in France. We did the cells at the lab level. We did some simulations of what could be achieved at the pack level with this open source program. And we, again, are on par with what you could get with some commercial lithium-ion batteries. And also we wanted to check on sustainability. So we were in touch with a Swedish group, which does calculation of different sustainability indicators. And in this case, one of the indicators they work with is the calculated natural capital cost, which relies mainly on the raw materials. So it does not focus on the processing of the materials, but just on the very beginning on the raw materials to know the basis. And in this case, we were comparing the sustainability of this technology with some lithium-ion technologies like graphite lithium iron phosphate, as I was mentioning, or graphite lithium manganese oxide, or another lithium-ion technology, which is lithium titanate and lithium manganese oxide, which has this compound as negative electrode, and then aluminum current collectors can be used due to the fact that this compound is operating at very high voltage. But then the problem with this technology is that you have very low energy density, because you have about a penalty of even more than 1 volt per cell. But having a look at this, it turns out that the main issue with sustainability is copper, that copper is really a problem. Here it is a calculation of how much it would cost to restore the environment from the impact of extracting those metals. So copper is the most problematic one. So in fact, one of the advantages of the sodium-ion technology in terms of sustainability is also the use of aluminum. And in fact, if we were able to get rid of vanadium, which is the main component here, we would even be better. But still, this is much better sustainability-wise than state-of-the-art lithium-ion. So in the framework of a French national project, where we'll be participating as foreign partners, it was possible to scale up that technology. So here you see the electrodes. These were the cells that were produced. Quite good cycle life for those cells, and also quite good power performance, which was unexpected. because it was really the first prototypes, but this sodium vanadium fluorophosphate really reacts with very fast kinetics. And with those cells, it was possible to make a pack. And this pack was used to power a robot. So this is this robot which is packed with this, which is powered by this sodium ion pack. So this was a while ago, and since then this technology has grown more. In the framework of a European project, we were able to scale this technology bigger, and then there is a sodium ion battery also in a substation from the Catalan company Estevanell Energia, close to Camprodon. And finally, there has been also a startup company in the north of France, which was established in 2017, and they are really working hard to improve this product. But this is not the only startup in Europe dealing with sodium-ion batteries. There is Faradion in the UK, who started way earlier. And in this case, they are using those layered electrode materials that I was mentioning. And again, they are on par with lithium-ion batteries. And this is some of the modules they manufacture. And they are using this in electric bikes. So far for the sodium ion concept, here you see that the TRL level of this technology is rather high, and the progress has been fast as a result of the chemical analogies between lithium and sodium. And so now we go to the other side of life, which is, in this case, it is the calcium metal batteries. Those are in their infancy. We are struggling to prove the concept and to enhance TRLs. And the issue here is that nothing can be taken for granted, and the know-how from the lithium-ion technology can seldom be used due to the chemical differences between lithium and sodium. So you may have heard of these technologies rather recently, because it is rather recently that most of the papers have achieved, but the ideas are older. So the first use of calcium in batteries dates to 1935, but this was used as an additive to lead for lead acid batteries. So in the 60s, the idea of using calcium as electrode material, especially for primary cells to be used in military applications, came. So you see the timing. So it was right where those military applications were really interesting. And then there were some papers published and so on, although the mechanisms and the chemistry behind was not really well studied. Then in the 90s, there was a rebirth of the interest of calcium batteries. And then because there was this battery technology, which is commercial, lithium thionyl chloride technology, which is a primary technology again. And it was suggested that using calcium instead of lithium would be an improvement for the cell safety, because upon cell reversal, it would not be possible to plate lithium and to have lithium dendrites, because plating of calcium was not possible. And another advantage is that calcium has a higher melting point and a higher conductivity. It did not make it to commercialization, and it stopped there. But the idea that plating of calcium was difficult remained, and this was deemed to be due to the fact that those passivation layers that are formed at the negative electrode, the electrolyte interface, do not enable transport of calcium to ions. So we did some calculations about really the practical prospects of such technologies. So we took this Excel file, which is given in this publication, very simple calculation, just mimicking what is technologically known from the lithium-ion technology. In this case, for the positive electrode, which we would expect would be similar, would be a tape-casted electrode with an oxide, a binder, and carbon black. So the density, the porosity, and so on are taken from there. Then we are supposing that we use calcium metal as the negative electrodes, and then this is what we calculated. So we suppose that we can find a positive electrode material that would operate between 2 or 4.5 volts and would have different values of capacity, 50, 100, 150, and so on. For instance, if we're able to develop a material which has a capacity of 150 milliamps hour per gram and that works at 3.5 volts, we would be on par with the best lithium-ion battery technologies at the moment, the highest energy density, the NMC graphite. This graph is volumetrically, this one gravimetrically, but results are the same. And this is not really such a huge value. But the thing is that even if we were successful, we would be able to have very good performance. The field has not been developing, mainly because what I was mentioning, the general thought that calcium deposition was not possible. This was again stated in this paper in 1991 by the group of Doro and Auerbach, who were the pioneers in the development of the magnesium batteries. And they tried to deposit calcium from organic electrolytes, and their conclusion was that it was not possible due again to the fact that this passivation layer would never conduct calcium ions. So then if you don't have an electrolyte which enables calcium plating and stripping, then it's very difficult to focus on the cathode development because it's very difficult to test those materials. So there were some studies about calcium intercalation in those materials, but not much. And this was what really limited the technology. So back in 2015, we became interested in this field, and we said, okay, why there is so few works about calcium? So we were interested because of the possibility of good performance, of the sustainability and so on, but also because of scientific curiosity to see what was the issue here. So the first question why is it not possible to develop to plate calcium ions? It is because the migration of solvated calcium ions in the electrolyte is a problem, or because desolvation at the surface of the negative electrode is an issue, or because, as this was pointed out, the transport of calcium through the passivation layer does not take place, or finally it is a problem to nucleate on the surface. And we started to work on this topic, and we realized that the main issue was the formation of ion pairs in the electrolyte due to the fact that calcium has a 2+ charge. And this formation of ion pairs was limiting migration of calcium in the electrolyte. And just by increasing the temperature to 100 degrees C, we were able to see calcium plating and stripping. This is a conventional salt, and the conventional solvents like those used for the lithium-ion technology. And here you see some cyclic voltammetry experiments where you can see that the plating and stripping takes place. This is an image of the deposits, but of course 100 degrees C is not very practical. And again, we have a problem with the efficiency of this deposition because there is also electrolyte decomposition, and especially this is also enhanced by this higher temperature. But here there is a benchmarking on lithium and calcium anodes. So here you can see calcium-calcium symmetric cells at 100 degrees C. You can see that they work fine. The only issue is that the polarization between oxidation and reduction is very high. And here you have lithium-lithium symmetric cells to compare at room temperature. And you see that really this is much lower. But still, it is really a starting point. So after we reported on those results, other electrolytes have been suggested to be viable for calcium batteries. This is the first by the group of Peter Bruce. In this case, they are able to plate calcium at room temperature using this electrolyte in a tetrahydrofuran solvent. The main issue here is that the stability of this electrolyte upon oxidation is not very high, so you will not be able to use cathodes operating at beyond maybe 2.5 volts, but the efficiency is rather good. And one issue is that as soon as it is deposited, calcium starts to react with this electrolyte and also form a calcium hydrate layer. And more recently, independently by two groups, also other salts have been proposed, also containing boron. And in this case, they need some additives or some preconditioning to be able to achieve efficient plating and stripping. So, well, nobody's perfect, but still we are starting to have some different kinds of electrolytes which prompt us to optimism. But it is really very, very tricky to develop those compositions. So once we had the electrolyte, which was enabling calcium plating and stripping, we wanted to look for cathodes to prove the concept. And in fact, one of the advantages of this electrolyte is that it is compatible with high voltage cathodes, even at 100 degrees C. And the first thing is the development of the protocols. And we had a lot of issues with that. If we were working on the field of lithium ion, we would simply test our potential materials against lithium metal, in which is termed half cells in this field. But in our case, I have told you that the calcium anode is an issue and they have a lot of polarization. So this is not really a cell setup that you can be using, because it would not be reliable, because this calcium counter electrode may mislead the results and you will not really be sure on which potential window you're testing your material. So you're forced to use 3 electrode cells. And then the issue is which is the best reference electrode, and this is not trivial either. We started using calcium metal, but then we need to calibrate it because there are some relevant differences between what would be expected from the standard reduction potential to what we observe. But once we had developed all those protocols, we were ready to start testing materials. And we focused on 2 types of compounds. First, traditional intercalation hosts like V2O5 or TiS2, or other compounds which would also contain calcium in the crystal structure, and basically calcium transition metal oxides. This is our playground. And essentially what determines the theoretical capacity and the potential is the composition of the compound, which is the transition metal, which is the redox center, and also which are the counter electrodes and the covalent or ionic character of this bonding. We can look for compounds having or not having calcium in the crystal structure, because we have calcium metal in the anode. So this is the source of calcium. It's not as in the case of the lithium ion technology, where lithium needs to be supplied by one or by the positive electrode, for instance. And another relevant thing is that the compound that has to be used as cathode has to enable migration of calcium within the crystal structure with good kinetics, which means migration barriers lower than 0.5 electron volts, or at least lower than 0.7, which is not trivial. Other cathodes one could think of are organics, and in this case, there is some people starting to work with organics. The main issues would be the same that we find when trying to apply organic materials for lithium-ion technology, that stability, low density, or solubility in the electrolyte, but they have the advantage that they are easy to process and low cost. And of course, one could think of more exotic concepts like calcium oxide or calcium oxygen, or calcium sulfur. But these are concepts which are not yet solved with lithium metal as anode, so also tricky ones. So in our case, we naively focused at the beginning on perovskites, because as you know, this is a very rich family of calcium transition metal oxides. And we collaborated with Elena Arroyo at Universidad Complutense de Madrid to do some DFT calculations, and it turned out that the molybdenum perovskite would be very interesting in terms of potential. And we were able to prepare it, but then when we tried to extract calcium electrochemically, it was not possible. And we understood then when she calculated the migration barriers for calcium in the structure, which are rather high. Then we became interested in the calcium Mn2O4. This compound had been studied by the group of Christine Persson. They did some modeling. They assumed that a calcium manganese 2O4 spinel could form. And if it could form, the migration barriers for calcium would be rather low. And this is understandable because calcium would be here in a tetrahedral coordination, which is not really expected for calcium. Calcium is too big for that. So that's why it would have tendency to migrate. And in fact, this polymorph has not been able, nobody has been able to prepare this polymorph, and the stable polymorph is the Marokite one, which is this one, which we were able to prepare, that has some channels in the crystal structure, along which maybe calcium could move. This is the electrochemical attempt to oxidize this compound. We see this plateau at high potential, which coming from the lithium-ion battery field, one could think, oh, maybe this is the oxidation and this is irreversible. But in fact, when doing X-ray diffraction, we realized that nothing changed, and this is simply electrolyte decomposition. And again, we understand this because when we calculate the migration barriers, they are really very high for this crystal structure. So then we became interested in those compounds, which are derivatives of the hexagonal perovskite. And these are the simplest compound is this one, calcium 3 cobalt 2O6. The crystal structure is made of columns of cobalt octahedra and trigonal prisms sharing faces. And in between those columns, there are calcium ions, and those compounds have been studied a lot for their magnetic properties. So they are really very easy to prepare. And when we try to oxidize and reduce electrochemically, this is what we get. There is a huge polarization between oxidation and reduction, which is indicative of not very good kinetics. But luckily, when we do X-ray diffraction, we see that something is going on here in black. This is the pristine compound. Then when we start oxidating, some regions of the pattern really change a lot. And here at the end of oxidation, we have a new phase, which seems to be pure. But then when we try to reduce, nothing really seems to happen except for the increase of this peak, which corresponds to calcium fluoride, which is due to the decomposition of the electrolyte, and not even if we go to higher temperature. So first question is, are those changes related to the extraction of calcium? Because we see that in some regions the pattern changed a lot, and in some other peaks remain almost unaltered. And we were able to find a model for the crystal structure of the oxidized compound, looking at other members of the same family of compounds. And this has an incommensurate crystal structure with two periodicities for the C, with two C-axes, one showing the cobalt periodicity and one showing the calcium periodicity. And from the Rydberg refinements, we were able to refine the occupation of calcium in the crystal structure, and it was clear that we were able to extract calcium electrochemically. But unfortunately, as I was mentioning, this process is not reversible, at least with the electrolytes we have tested. So coming to conventional intercalation compounds, we were revisiting V2O5. This is the crystal structure of V2O5. And interestingly, there is a compound that has been reported to and prepared by solid state synthesis, calcium V2O5, which has a very similar crystal structure. So we naively thought that we could electrochemically intercalate calcium in this compound very easily. And in fact, there had been in the past some reports of potential calcium intercalation in V2O5. There was even an X-ray diffraction pattern given despite no elucidation of the crystal structure. But the thing is that this electrochemical, this diffraction pattern has nothing to do with this compound. And in our hands, we were not able to intercalate calcium into V2O5. And we got this pattern when we had water impurities in the electrolyte. So we really believe this is a result of proton intercalation in V2O5. And this is similar to some vanadium bronzes. And then we decided to to do the opposite. Let's prepare this compound and let's try to extract calcium from the crystal structure. And again, this was not possible, neither electrochemically nor chemically. So, and the same was true for magnesium. So the message here is really that impurities in the electrolyte can make your life very complicated because protons are very mobile. So then finally, we also studied TiS2. This compound has been studied a lot from the early days of intercalation. And here there is a paper from 1974 from the group of Jean Rouxel in Nantes, where they were able to intercalate calcium in TiS2 by immersing this compound in a solution of calcium in liquid ammonia. At the beginning, ammonia was co-intercalated with calcium, but then by gently heating, they were able to remove the ammonia. And then they even suggest some crystal structure for these for calcium between the layers that they believe it's octahedral. Then, apart from that, there was also a paper by the group of Anton van der Ven in Santa Barbara who did compute phases which would have different ions between the layers: lithium, sodium, potassium, magnesium, and calcium. And he was computing also which would be the most stable coordination for those ions. And in the case of calcium, it would be either octahedral or prismatic, they suggest, depending on the amount of calcium. In our hands, this is, we took TiS2, we reduced and reoxidized in calcium cells. This is the X-ray diffraction pattern. So from the very beginning, we see peaks at low angles. There seems to be more than one phase form, so probably there is a kinetic issue. But then when we reverse the current, we are able to oxidize and to recover TiS2 again. So the process seems to be reversible despite with large polarization, so far to be commercially interesting for the moment. The fact that there is also some unreacted TiS2 means that there is also an issue with kinetics. Those are the three phases that we were finding. The first one has a very huge interlayer distance, and we believe that it corresponds to calcium intercalated together with some solvent molecules. The second one seems to have the same cell parameters as reported by Jean Rouxel for calcium 0.5 TiS2. And about the third phase, we are still not sure. It could be a stage 2 phase. But in any case, this is reversible, despite it's not really practical at the moment. So in this case, we had three phases. We were not able to refine the calcium occupation. So we really wanted to make sure that calcium went inside the crystal structure. So in this case, we looked for complementary characterization techniques, and luckily enough, we were able to do synchrotron experiments at ALBA and do some transmission X-ray microscopy at the calcium LH and do some tomographies of the particles. We use a standard, the pristine TiS2, and also some compounds that can form as a result of the electrolyte decomposition as calcium fluoride or calcium carbonate. And this is what we get. So this is the particles, and the calcium density here could correspond to some sort of calcium carboxylate. Then this density of calcium here underneath would be in agreement with calcium carbonate. And finally, these pink bubbles correspond to calcium ions inside the TiS2 particles. So we really confirm that calcium is inside the structure and this is reversible. So as I was mentioning, this was not very practical results, and we were looking at the influence of the electrolyte and the influence of temperature, because it is not really practical to operate at 100 degrees C. But there are not that many available electrolytes, and the issue is that if we use calcium anodes, we need to use an electrolyte enabling calcium plating and stripping, because when you reduce the working electrode and you intercalate calcium, you are stripping calcium from the counter electrode. But if you want to test reversibility, then you need to extract calcium from the positive electrode and plate calcium. So we decided to split those problems and get rid of the calcium counter electrode for the moment and just focus on the titanium. And we use activated carbon as counter electrode. This is an electrode operating via a capacitive redox mechanism. So the main issue here is that the capacity is very small. So you need to use a huge excess of negative electrode. So the balancing of the cell is tricky. But by doing this, we were able to see calcium intercalation into TiS2, even at room temperature. Working with calcium TFSI as electrolyte in propylene carbonate. And we don't see the phase number 2. So in this case, with this electrolyte, only phases 1 and 3 are formed, which is something we're still having a look at. You see that we can do even some cycling at room temperature. Polarization is still huge, so there is still a lot of things to improve, but we are currently working on that. So finally, just the take-home message for people interested in developing new battery chemistries in general and multivalent systems in particular is that nothing can be taken for granted. I mean, if you're coming from the lithium-ion battery field, you need to believe that nothing is reliable. Many side reactions can take place. You need to use counter electrodes that have a well-established redox behavior. You need to ensure that they have excess capacity versus the working electrode. You need to have a reliable reference electrode. There are many reactions that can involve the electrolyte that can give some electrochemical response, which you may mislead as coming from your electrode material. This is a summary of, in a review that we wrote recently about calcium batteries, a summary of all publications reporting potential cathodes and be critical when reading those papers, because in some cases, just no complementary characterization techniques were used, and then the authors were misled by the response, which may be due to side reactions. As for instance, here you have a paper reporting that what they see is the current collector corrosion. So as simple as that. So finally, the strong message is that for multivalent batteries, you need to do a very careful definition of research protocols with blank experiments. This is simply aging of V2O5 in one of the electrolytes we use, and you see that it is reacting even in absence of current. Work with 3 electrode cells to have a reliable reference electrode and use complementary characterization techniques. And finally, I always like to end with this table, which was given by Ralph Roth, which was one of the pioneers in lithium-ion battery research, about the timing that is needed for battery technologies to go from the concept to the market, because there are many steps that need to be fulfilled. It's not, it's like in pharmacology, you need clinical trials, so it takes time. So it's those technologies that we are starting to develop today will not be in the market tomorrow. It would take at least 10 or 20 years, but still I think it's worth the effort. So I'm optimistic as Walt Disney used to say. So finally, just the acknowledgements to people that participated in the work from ICMAB, Alexandre Ponrouge, who is now a permanent researcher, Carlos Frontera, who is a specialist in diffraction, and then other postdocs and master students, and also collaborators, Patrick Johansson from Sweden, Elena Arroyo from Madrid, Andrea Sorrentino from Alba, Patrick Rosier from Toulouse, and also Fanny Bardet from Toyota, because we were lucky to start in the field of calcium with a project funded by Toyota, and also to the European Commission for funding of those activities. And thanks to you for your attention. And with that, I'm happy to take any questions. Thank you.
Thank you very much, Rosa, for this wonderful overview of all the technologies. I'm really impressed by all this. And now the floor is open for questions. So please, if someone has questions, you have the questions and answers. Otherwise, and I hope that that Judith, that is in the background, will collect those. If I will start myself, because there's, I'm a theoretician, and many of the theoreticians are making these huge databases with lots of properties of potential materials for batteries, particularly. I mean, for many processes, but particularly for batteries. Is there anything that you find useful, or how do you use those, or do you think that we will ruin your lab work, or how can you comment a little bit on that?
Yeah, I must say, for instance, when dealing with the materials project, which was developed in the US by Christine Persson and Gerd Cedar, I was pretty impressed at the beginning about what theory had to offer. And I really think it's a very valuable tool for us when exploring potential materials. You can just go there and see compounds that have been already reported, what properties they would have, or even virtual compounds. I mean, if a compound is known with zinc, but maybe magnesium has the same size as zinc, so maybe you could prepare the magnesium derivative. So this is very useful. So you can predict the potential, you can predict the migration barriers, which I think is less straightforward, is predicting kinetics. This, I think, is much less cumbersome. And also interaction with the electrolyte or possibility of side reaction. So I think it's really very relevant tool, and especially those efforts to create those databases open to everybody, because this can be really very useful. And I think that theory still cannot predict everything, but I mean, what they can predict, or what you can predict at the moment, is already very helpful.
So JR, thank you. JR has a question. JR,
yes. Can you hear me? Hi, Rosa. Thank you very much for this talk. I mean, really interesting and inspiring. I mean, I am completely ignorant of the battery field. So, but looking at your analogies from lithium to other batteries, I wonder why cannot you go smaller instead of lithium cation proton battery? What's the problem with that?
In fact, there is, I mean, the nickel batteries that you may have used in the past, but now they are used in the hybrid, non-plug-in hybrid vehicles like Toyota Prius or Yaris or so. Those are proton-based batteries. The issue there is that for proton, your electrolyte solvent is water. So you use, I mean, and the first battery technologies to be developed were based on water because it was the solvent more readily available. And the problem with water is that your electrochemical window is rather narrow because, I mean, in theory, the thermodynamic window is 1.23. So you cannot go above or beyond because then you release hydrogen or oxygen. So then the issue is that when you want to go to higher cell voltages, so use materials that react at higher or lower voltages, you need other solvents, which are much more stable towards oxidation and reduction. And this is when you use those organic solvents that we were mentioning. And protons there are not, so finally you would, if you started using a salt that would release protons, you would again release hydrogen upon reduction. So the problem of protons is hydrogen, even if you were using an organic solvent.
Okay, thank you very much.
Okay, any more questions from the audience? You can post them through the questions and answers. Don't be shy.
People are hungry.
Yeah. Well, yeah, so I have many more, but so related to these intercalation systems, I mean, how do you operate in the real, I mean, how do you select the new material to try, or how do you, because I have seen, yeah, you know, vanadium oxides are prone to do this, titanium sulfides are prone to do this, but how is the logics behind, or how do you operate on this?
Yeah, so the first step would be what we would call chemical intuition. So you need something that is able to oxidize or reduce. So typically you would go for a transition metal because they have a very wide range of stable oxidation states. And then from experience, you know that the reduction potential for the couple titanium 3 or 4 is lower than for the couple nickel 2, nickel 3 or nickel 3, nickel 4 or whatever. But now, I mean, this was before, but now, for instance, with the material project database, you can just enter there and from a well-known crystal structure, you can simulate which is the voltage. So which goes a little bit beyond the chemical intuition, because then depending, I mean, the redox potential of this transition metal will in turn be tuned by the crystal structure and also by the ionicity of the bonding. So if it's a more ionic bonding, and you have a fluoride, for instance, the potential will be higher because the Fermi level will be lower, and the opposite. So this is something that you can qualitatively predict from knowledge in chemistry, but then of course for quantitative prediction, then theory is really very useful, and all those databases that you were mentioning earlier for sure as well. Yeah.
Okay, we have a question from Anna. So yeah, Ballesta.
Yes, hello. Congratulations on the talk and on your work. It was really educative. My question goes a bit in direction graphene. I guess all of you heard about it. And it's, did you consider to use graphene in the development of the new batteries?
In fact, what is very successful in the field of lithium-ion batteries is stacked graphene, so graphite. Graphite has been from the very beginning present in commercial lithium-ion batteries, and graphite has an advantage over graphene, which is that it is much more dense, so you have much higher capacity per volume, and also that the surface area is much smaller, so then you have much less reactivity with the electrolyte. So as an electrode material, I think that graphene will never beat graphite. Then what I have seen useful for, at least what I have seen for the moment, really useful for graphene is the use as additive, for instance. I was mentioning that to prepare the electrodes, you tape cast a mixture of your active material, carbon black and binder. Sometimes graphene may be useful as an additive because it has a high surface area and is very conductive. So if using graphene, you can decrease the amount of additive from 3% to, or from 5% to 2%, whatever, then it would be interesting. But as an electrode material, it wouldn't have, I don't foresee any future. It has been used also in lithium sulfur batteries because sulfur is very insulating, and they need to mix with carbon, and then also as a substitute of carbon there. But yeah.
And sorry, one extra question. And instead of normal graphite, like pyrolytic graphite, for example, something like turbostratic graphite, where the distance in between the planes is a bit larger, so that it's easier intercalation?
Yeah, well, the fact it may have an influence on the intercalation on other ions. I mean, lithium works pretty well with graphite, and they are using they are using natural graphite as well, which is much cheaper. They are using sometimes synthetic graphite, so they try to make also some spheric particles, like treating the even natural graphite to do flakes. But it's the interlayer distance is not an issue because it can be expanded very easily. For intercalating larger cations, then you need to check, because graphite does intercalate potassium, for instance, but it does not intercalate sodium because of some geometrical aspects. And if you do the FT calculations, you will see that the fit is not really good. So that's why those turbostratic material, or in the end, the very disordered materials like hard carbon, they are used for intercalating sodium. But yeah, I think carbon engineering is really something which could be interesting for the field of sodium-ion batteries, because it has not been developed that much for the field of lithium, because the graphite works very well and it's very cheap. But yeah, with sodium, you may have a point there. Yeah.
Okay, thank you. Thank you very much.
Thank you, Anna. Thank you, Rosa.
Thank you.
Any more questions? Otherwise, I have a final question, and this is related to all the fuss that has been in the news about this potential plant in Polonia about batteries. I mean, can you comment a little bit on how you see the research there and the field? How do you feel that the field is going to grow? Or
yeah, in fact, it's funny because of course, I mean, historically, batteries were born in Europe with Volta, Royal Society, Napoleon funding Volta, so everything a pretty European perspective. Then really the technological development, it came to the US because in the 70s and so on, they were starting to have problems with pollution and in big cities, and they blamed this on the cars. So car companies were starting to think, would the batteries be a possibility? Then they had the oil crisis. Big companies had a lot of labs for R&D research, and then there was this technology. They started to build the lithium cells. Then it moved to Japan because then the portable electronics were starting. They were needing a battery technology to power that, which was not toxic. They could not use nickel cadmium. And then nickel metal hydride was born more or less at the same time that lithium-ion technology was born. And then this was a very successful marriage, so to say. But then portable electronics is small batteries, so they are shipped with the devices. If we go electric, then we have a problem because not everything can be produced in Asia, and shipping batteries is not safe. So then finally, if you want to go electric, really electric, you need to produce the batteries close to the place where you produce the cars. And at that moment is where I think that Europe has very fast entered the game. And there was no battery production in Europe. And now every day we have an announcement of a new plant in Poland, in Sweden, in Spain, wherever. And there are two types. I mean, some of them is technology that comes from Asia, and they just install the plant here just to power the vehicles that will be fabricated in Europe. Or others, just companies like Northvolt in Sweden, which is aiming at developing their own technology, and they build to build very green batteries because they have a very green electricity there with a lot of hydropower. So I think that the field is really moving because of this importance of the car industry in Europe. And I think that since cars are big, and you need big batteries, they need to be produced rather close to the place where cars are produced. So I don't know where in the end a company will be built in Martorell or far away from there, but I don't think it's really advisable to do it very far away. And of course, as Volkswagen has already joint ventures with LG, so I think that if they are really going to produce electric vehicles at SEAT, it is plausible that an LG factory appears somewhere close to them.
And do you think that this will help us? I mean, having research funds for
I don't know, because I think that if it is a company which is based in Asia, I mean, LG, they have their own research labs and so on. They may need something else locally. I mean, when they define what type of packs and so on they have to do, they need some post-mortem studies for dead cells, or they need then they may rely on us because it may be easier to create a small ecosystem of support around them. But I think that or they may subcontract some specific studies, but I mean, they will have their core based in Asia or in their country. Then it may be, if we have some contact with them, because we do some of those works for them, then something else can pop up. For instance, we had this project with Toyota, which was absolutely a risk project. I mean, you have seen the degree of progress of calcium batteries, but they, as a big company, they are interested in having patents on new technologies. For them, is like they want to have some IP in new concepts. So in this case, it was good for us because it enabled us to develop something from scratch, and also for them. So for sure, having them closer, it will be good. But still, we shouldn't be naive and think that then we will save their concept, because this is not the case. But still, it will be positive for sure.
So thank you very much, Rosa, particularly for this final discussion, because I think that this is very good for all the students that we are having in the seminars. And I hope that you can visit us soon in person, as soon as things can go back to normal. And thank you very much for that.
Sure, we'll be glad to come. Thank you very much for having me, Nuria, and the ICMAB team. Yeah, thank you.
Bye, everybody. Ciao.
Bye.